Very good evening, everyone. Good evening, Miss Arushi, and good evening, Myra is also there. So, once again, a warm welcome to each and every participant over here. I would request you all to please switch on your cameras so that I can see and we all can uh, at least interact properly. Everyone, please switch on your cameras. Okay, so my name is Kriti, and today with us we have our special guest, Miss Arushi, and our host, Myraa Khattar. Okay, so let me just tell you quick things about Miss Arushi. So she's a leading astronomer, okay, with having actually she's a young brilliant young astronomer and expert on near earth asteroids. Okay, so she is with us to share her insights about about the asteroids and take us to the fascinating world of the asteroid. Along with Miss Myraa Khattar is there, so she will be our host today and she will be asking some questions and telling us some things related to asteroids. So over to you, Myra.
All right, sure. Greetings, all space enthusiasts and those who still think Pluto is a planet. This is Myraa Khattar, and I'm going to be your host for this evening. It's not going to be a regular evening, of course. This is a spectacular evening because we have Miss Arushi with us. Today, we have the story that is out of this world, and we're going to pay a visit to Miss Arushi. But before meeting her or interacting with her, we need to know about her, like who is she, what she has done, and believe me or not, she has done a lot in the field of space and technology. Arushi is a grade 9 student and 2023 Young Astronomers Award winner of the Royal Astronomical Society of Canada. Yes, folks, it's a lot to digest, I know that. While some Gen Zs and some Gen Alpha kids were busy deciding what to watch on Netflix, Arushi was busy winning awards and potentially planning humanity' future in space. Over the years, she has built robots, battle bots, rockets, rovers, you just name it. It's just a whole list. She participated in over 50 hackathons. 50 hackathons. And if you ever want to visit a museum that is full of trophies, medals, certificates, Arushi's workplace is the right place to see such beauties. Of course, you have to take her permission though. While most children think about how to wisely spend each Robux in their avatar creator on Roblox, Arushi thinks wisely how to build such simulations like Roblox and Minecraft and 3D models for everybody to access. Furthermore, she won 2020 NASA Space App Global Award, and that's a big thing to be honest. While the whole world was figuring out how to bake banana bread without actually setting off the smoke alarm, and I mean, Mr. Google was tired enough with all the messages that he was getting about banana bread. Arushi, on her own, was figuring out how to make rockets take off without setting off their smoke alarm. But wait, just please hold your horses and don't let them go because we have much more to hear ahead. And the horses might also do a little neigh on that as well. Her latest project is a real blockbuster, my friends. Arushi has a special passion for space and astronomy. Her project developing algorithms to determine asteroids' physical properties and success of, as we know, the whole world knows, NASA's DART asteroid deflection mission won the Best of the Canada-wide Science Fair 2023 award. Now that's a lot, right? Let me just break it down simply. So she won the Best Canada Science Fair Project 2023 award with the success of NASA's DART asteroid deflection mission that she worked on. But Arushi's talents don't stop at Canada's border. It's just not like the soldiers are like, hey, Arushi, that's it. She has gone beyond that. She represented Canada at 2023 European Union Contest for Young Pure Scientists in Brazil, Belgium. among 130 participants from 36 whole countries. And Arushi was the youngest at just 14 years old. She was the youngest. That's just so amazing and overwhelming. And guess what? Her project actually won second core prize. I mean, that deserves a big round of applause, be it virtual, be it physical, of course. I bet other contestants are still Googling as we speak how to beat Arushi, a beginner's guide. When she's not busy with astronomy related challenges, keeping herself busy on a computer or just searching about astronomy, Arushi uses open data for civic research and advocacy. So the girl is also in advocacy. That's just a true gem, to be honest. She regularly makes deputation to the local and provincial governments on a range of issues. And I think Arushi is a better person to tell on what type of issues. And I'm personally pretty intrigued to know what type of issues she discusses. She's probably one of those teenagers who text the mere doesn't leave on read. The mere like 100% replies to all of her texts because they're just so great. Attention, s'il vous plaît. You might be wondering why for all of a sudden I'm just speaking French and switching from English to French. Because budding astronomers are she's an excellent French communicator. And if you want to ever communicate with her in French, please go ahead and she's the right guide. Now, I have talked enough about Miss Arushi, and I just want to save a piece of cake for her to introduce herself and bond with you guys. So, Miss Arushi, it's time for you to share your valuable insights for the day, and the stage is all yours. Thank you so much.
Thank you so much, Myraa, for that wonderful introduction. So as all of you guys have heard, basically everything's covered, but my name's Arushi. I'm a grade 9 student. I'm from Toronto in Canada. So it's about 8:30 a.m. for me. I think it's gonna be evening for you guys. But it's so wonderful to be here, and today I'll get the chance to talk to you guys about asteroids. So I can go ahead and start my presentation. Just let me find my slides. So as you guys all know, we're very close to International Asteroid Day, which is why I thought this would be the perfect opportunity to talk about asteroids. So first, for those who don't know, let's get a quick introduction about what is asteroids. So these are small rocks that orbit around the sun. Normally they orbit in between Mars and Jupiter, which is where the main belt is. And these basically asteroids are more than to what meets the eye, because these are basically, you could think of them as capsules from the beginning of the formation of the solar system, because their composition has not changed since then. But most asteroids, as I said, were found between Mars and Jupiter. But these orbits are uncertain, so sometimes these asteroids can come close to the Earth, and that's what we call near-Earth asteroids. That's when they come in between 1.3 AU to the Sun. And that means their orbit can intersect with the orbit of the Earth at any time, giving possibilities of collisions. And asteroids have different shapes, different sizes, different materials. Asteroids have sizes ranging from tiny little pebbles that you can barely see up to kilometers and kilometers wide. One of the biggest asteroids is Ceres. Some other interesting asteroids that have had missions go to them is, for example, Bennu and Apophis, which are both around a kilometer. And you might be thinking, have spacecrafts visited asteroids? And the answer is yes. Spacecrafts from countries all across the world have been going to asteroids for the past decades. For example, from the United States, we launched a mission to go to the Bennu asteroid and try to get back samples, which was a success. In addition, there have been missions from the European Space Agency and China, and Japan. You may have heard of the Japanese um, Space Agency, JAXA. And actually recently, they launched the Hayabusa 2, which was able to get samples of the Ryugu asteroid. And now they're turning that mission back towards Apophis. And India and UAE are also planning space missions for the future, which is amazing. So you might be thinking now, can asteroids really collide with the Earth? And the answer is yes. Asteroid collisions have happened all the time. Actually, I'm going to play you a video which was taken about 2 years ago, where an asteroid actually came right next to my home city, Toronto. And you can see it go past the CN Tower. So now you can see it whiz past the CN Tower. And this was actually the seventh asteroid in history to be discovered before it impacted the Earth, which is amazing because it shows how far our technology advancements have gone so far. And guess what? As we speak today, an asteroid is coming so close to the Earth and making a close approach. This asteroid is actually quite large. It's 120 to 260 meters in diameter. And it's not just coming close to the Earth, it's going in between the Earth and the Moon. And this asteroid was only discovered a few weeks ago. And now it's on close approach. So we're probably all near the northern hemisphere, but if you're in the southern hemisphere, then you can even be able to watch it right now. So, why do I study asteroids? Well, there's two main reasons. First, as I've talked about, is planetary defense. I find it very intriguing that at any point an asteroid could make a close approach to Earth and possibly even collide. And these collisions might have a very small risk and almost zero, but it's not zero. And if we had an asteroid on collision course with the Earth that can give damage, we would need to know how to deflect it. And deflection requires knowledge of the asteroid's physical properties. But the second reason is because of the evolution of the solar system. Because asteroids contain minerals and materials from the early formation of the solar system. So understanding their composition can help us better understand how the solar system and the Earth were formed. But to study these asteroids, we first need to know where they are. So there's two main challenges. First is detecting unknown asteroids. Would you believe me if I said hundreds of near-Earth asteroids continue to be discovered every month? This is because there's so many asteroids in our solar system, we've only discovered a small fraction of them. Especially the smaller asteroids below 300 meters are likely to still stay undiscovered. Second, once we know where these asteroids are, we need to determine their physical properties. And this is a huge issue right now, because actually, more asteroids are being discovered than we can analyze their physical properties. And to analyze their physical properties, we need multiple photometry observations of this asteroid over long periods of time. And I'm not talking about days or months, I'm talking about years, actually 3 to 5 years is needed. So let's go on to the first challenge, detecting asteroids. So one thing we know about asteroids is that they move. Unlike stars, unlike nebulas, asteroids move. Which means if you take a picture of the sky at let's say 12 o'clock, and then 5 minutes later at 12:05, you take another picture of the sky, you'll be able to see a difference. So here you'll notice on my screen, I have two different images. First is an image you could save from your telescope, and second is from the star atlas. Your challenge is to see if you can spot an image from your telescope or an object in that image that's not in the star atlas. So I'll give you a minute to think about it and see if you spot any differences. Because something that you would see in your telescope and not a star atlas would mean it's potentially an asteroid. So just as a hint, I've kept two asteroids inside the image. I noticed someone raised their hand, so if you have an answer, please feel free to speak up.
Yeah, sure. So, before I spoke, I think someone was quick enough to annotate, and whoever did, yes, my option would be this. Like, in picture number one, you can see that there's this big, round black circle, and the second one is just not there.
So
So
great,
that
yeah.
is, yeah.
And you are in fact correct. That's actually one of the asteroids. So if you look here, in one of the images it's there, and one of the images it's not. And I have a small challenge for you. there's another asteroid that's very small in this image. So there's a second asteroid. So I'll give you guys another minute and let me know if you can spot it. Feel free to raise your hand or annotate again. Yeah, so if you have your hand raised, please feel free to speak up. And oh, perfect. I can see someone circled it here. And yes, in fact, you are correct. Wow, that's some great eyes to be able to see it. That is, in fact, the second asteroid. So congratulations, you guys were able to find the two asteroids. And that's really what my job is. And that's what my project was all about. So I'm just gonna clear the annotations. I don't know how to do that.
You just have to simply click on the pen option that you would see on your screen. There's a pen option. And once you find that, let me know. You just have to click on the eraser option.
Oh, perfect. Great.
Yeah.
I can see like three really small objects which are there in the star atlas, but it's not there in the image of your telescope.
Oh, really? Do you want to circle those objects so I can see them?
How do I circle them?
I think you can click annotate on the top of your Zoom.
Annotate. Where is annotate?
There's a pen option. Like once you move your cursor around or Arav, you would see a pen option, and once you click on that, it will show annotate. And then there's going to be a whole list of settings that's going to open for you, including the pen option.
I found it.
Yeah.
Okay, so I've seen you circled a corner here. And yeah, you are right. There is a lot of background noise in these images. And I can see you've circled this spot as well. And this is actually what we call noise. Because these images are not going to be perfect. There's going to be noise in the images, either caused by the camera, caused by the background light. And that's why you can see each background pixel is not completely zero value. It has some slight brightness to it. And that's what comes from weather conditions, it comes from the camera. And while we try to eliminate all of these noise by taking pictures in the camera in what we call dark frames, bias frames, which are basically taking pictures with the camera with the cap on so that we can remove all of the hot pixels, there's always going to be some noise that remains. And what you spotted is indeed that noise.
So how do you get the image like this when there's also darkness and do you like which type what do you use? Do you use radio waves? Do you use like normal light or do you use like X-rays? What do you use for finding these asteroids and discovering them?
That's a great question. And for the purpose,
Sorry,
I'll answer
Miss
this one
Arushi.
question.
Sorry, Miss Arushi, I am just
Yeah.
intervening in between. I'm requesting all of the participants so they can write their questions in the chat box. After the end of this presentation, we will allow you to take the questions of yours. So this will be more convenient. Okay, Arav?
Okay.
Thank you so much.
Perfect. And just to give a very short answer to your question, for my study at least, I focused on actually getting images. So this is not radio, this is not radio waves or anything. This is actually using pictures and telescopes and cameras to actually be able to take pictures of the sky and look at the objects. So moving on to the next slide. I'm just gonna remove the annotations again. So how do we find the asteroids in our image? Well, first we have to remove all of the known objects in our image to be able to eliminate all of them, because we know a star cannot be an asteroid. So what I did is I queried the Gaia database trace, which basically contains the position of all known stars in the sky. Using this, I was able to put this database onto my image, and all of the red circles you can see here correspond to stars. But that's not enough, because I also don't want to be detecting asteroids that already exist. So I used a second database called NASA Horizons, and this keeps track of the orbital motions of all known asteroids. But asteroids are a bit more complex. Asteroids are always moving. So how do we know where they would be in our image? And that's where the time factor comes in. By knowing the orbital motion of an asteroid, we can know its position at any given time. So by feeding in the time of my image using its file, I was able to find the position of all known asteroids. So what did I do after that? As I said, I wanted to eliminate all of these known objects. So what I did is I masked all of these known objects. I created black circles of custom radiuses around all of these objects that covered their brightness completely. So what was left was either noise or an unknown asteroid. So after that, I used a standard deviation algorithm, which was able to find all the potential asteroid candidates. So why standard deviation? Standard deviation was very useful in basically categorizing noise as well as asteroid, because noise is normally one bright pixel in the image, whereas asteroid is several bright pixels. So by using standard deviation, I was able to pick up that those several bright pixels and leave the one bright pixels alone. And on the right here, you can see these are two possible asteroid candidates that I've identified. And at the end of this project, I was able to find 3 preliminary asteroid designations using my algorithm, which was amazing. So now going on to the second part. We've been able to find asteroids, but now we want to know more about them. How big they are, how fast they move, how fast they rotate, and how do we do this? So this requires images of the asteroid over time, which is something we also call photometry, because by monitoring the changes in the light reflected by the asteroid over time, we're able to determine its physical properties. So when I say over time, I mean 2 things. First is over a long period of time. So this is 3 to 5 years. And this is where the phase angle of the asteroid changes. The phase angle is simply the angle between the observer, in this case the Earth, the asteroid, and the Sun. So, since the orbit period of these asteroids is 3 to 5 years, we need 3 to 5 years of observations. But why do we need observations at different phase angles? This is because different phase angles give us how different sides of the asteroid reflect light, which is essential for determining its absolute magnitude, which can later reveal its size. Second thing I'm talking about is short-term light changes. So this could be from a few hours to maybe a few days, and this is caused by the rotation period of the asteroid. Because most asteroids are not spherical, they're actually irregular in shape because they don't have enough gravity to pull themselves together. So, as they rotate, different sides reflect different amounts of light, causing 2 maximas and 2 minimas in their light curve. Using these light curves, we're able to find the rotation period. So how did I do this? First, similar to the previous methodology, I found all known stars and known asteroids in my image. So, as you can see on the right top side, this is my final result. And I was able to find my asteroid of interest. In this case, it was Didymos. You guys might remember Didymos from NASA's DART mission, which happened about 2 years ago, where they impacted a kinetic impactor onto the moonlet of an asteroid to try and change its orbital period. So for this purpose, this was my asteroid of interest. So next, I want to find the brightness of the asteroid in my image. So how do I go about that? Well, first I had to create an inner aperture around the asteroid, and this was to measure the pixel brightness of the asteroid itself. But that's not enough, because you might recall I talked earlier about background noise in my image. So how do I remove this? Well, the good thing is background noise is consistent across the image. So I created an outer islandless right around the asteroid to measure the background noise. Then, by subtracting this background noise from the total asteroid brightness, I was able to find its pixel brightness. And you can't just choose any aperture size. This size must be carefully crafted, because if it was too small, as you can see in A, it doesn't cover the full brightness of the asteroid. If it's too big, like B, it gives too much background noise and can lead to inaccurate results. So slope analysis and median was used to find the right aperture size. But my observations could be very long. Like I could be taking image after image for a few hours. So you might think, what could change during this time period? And the biggest change would be weather conditions. Stuff like clouds could come in, air mass could change, there could even be differences with the camera. So how do I actually remove all of these changes? This is where comparison stars come in. I chose 4 to 7 comparison stars in my image. These are stars with known and constant brightness. By measuring their change in brightness caused by weather conditions, I was able to apply these adjustments to the asteroid's brightness to get its computed magnitude. But this wasn't enough, because asteroids are also always orbiting around the sun, which means their distance from the sun and from the Earth is always changing, which causes changes to their brightness. Like an asteroid, which is right next to us, will seem much brighter than an asteroid which is light years away. So, I was able to apply offsets to benchmark the brightness of the asteroid to 1 astronomical unit from the Earth and 1 astronomical unit from the Sun, yielding its reduced magnitude. Fifth, now that we had the reduced magnitude, now we could actually measure the change in the brightness caused by phase angles. And this is where it becomes interesting, because from small phase angles, from phase angles 0 to 7, there is a huge surge in the brightness of the asteroid caused by the opposition effect. Whereas, from angles above 7 degrees, you can see that the phase curve becomes more linear, as you can see in this graph to the right, where you can see a reduced magnitude over a changing phase angle. So, you might think, how did I get these years of observations? Because 4 or 5 years are needed. And for this, I've used open sky surveys. So these are surveys that look at the sky every night and cover the full sky. So that means that my asteroid was very likely in these images. So by looking at the Sky Survey archive over several years, I'd be able to pick up all the images where the asteroid was located and be able to find its brightness. So now that I had the phase curve, if you look at the phase curve at the phase angle of 0, and you look at the reduced magnitude at that stage, that's what we call the absolute magnitude, the reduced magnitude where the phase angle is 0. In addition, I'm also able to determine this linear slope or slope parameter g, which is basically caused by the linear portion of the line, and it's very essential for determining the change in absolute magnitude over time. So sixth, now that I had the absolute magnitude of the asteroid, I plotted it over time and used my dense observations. So these were the observations taken in short periods of time, and this was used to find the rotation period of the asteroid. But not just that. You may remember Didymos was a binary asteroid, which meant it had a moonlet orbiting around it. This meant, how do we find the orbital period of the moonlet? So to do that, first I subtracted the rotation period from the composite light curve, and then I repeated a similar process to finding what the mutual orbital period would be. And that process used root mean square error and congruent modulo. So when I had my light curves, I folded them onto each other with different periods and found a period which had the best fit and lowest root mean square error. So results. I applied the 6-step methodology to Didymos. I was able to find its absolute magnitude to be 18.14 and G 0.16. And this was using ALTEF, which is an open database where citizen scientists put their observations, as well as ZTF, a sky survey. Second, I was able to determine the asteroid's geometric albedo or surface reflectivity using the absolute magnitude. Using geometric albedo and absolute magnitude, I was able to determine the size of the asteroid. And I found it to be 840 meters. Third, the rotation period of asteroid. So as I mentioned before, I fit my observations to different rotation periods, from let's say 2 to 10 hours, and for each, I calculated the root mean square error. So you can see, for example, here, if I fitted it to a rotation period of 3.4 hours, the root mean square error was quite high. Similarly, for 4.63 hours, it was quite high. But the best fit I found was 2.26 hours, where the root mean square error was the lowest, and this was the rotation period of Didymos. Second, after subtracting the rotation period, I followed a similar process and found the mutual orbital period of Didymos to be 11 hours and 55 minutes. And guess what? After NASA's dark impact, it reduced by 35 minutes. So what does this 35-minute decrease mean? So a 35-minute decrease Post-impact, using Kepler's third law, translated into a 40-meter reduction in the orbital radius, of the asteroid, proving that the deflection was indeed successful. And if an asteroid were ever on collision course with the Earth, we now know that the kinetic impactor method has worked before. Second, using the rotation period and the size of the asteroid, I was also able to determine its strength. Because if asteroids rotate very fast, with a rotation period below 2.2 hours, they're very likely strength bound, which means it's a single rock holding it together, because else it would fly apart. Whereas if asteroids have a rotation period over 2.2 hours and a size over 150 meters, they're very likely rubble piles, which basically means several rocks, tiny rocks held together by mutual gravitation. And this is actually the most common type of asteroid. Because I applied my algorithm to sample 10 asteroids, lots of them mission asteroids, binary asteroids, and I found them all to be rubble-based, including Didymos. Third, this wasn't enough. I applied my algorithm to determine the physical properties of different targets of space missions, binary asteroids, and even understudied asteroids. And for each, I was able to find all of their physical characteristics, like their size, absolute magnitude, rotation period, mutual orbital period if they were binary asteroids, and strength. And after this, you may remember my second goal was to be able to find the compositional diversity or the evolution of our solar system. So to do this, I applied my algorithm to thousands of asteroids in our solar system. And why did I do that? This is because from the albedo or the reflectivity of the asteroid, we can find their composition. Asteroids with low albedos are likely to be carbonaceous asteroids. Asteroids with moderate albedos are likely to be silicaneous or metallic, while asteroids with high albedos are likely to be ancestite or chondrite. So, knowing the albedos of these thousands of asteroids, I was able to find their composition. Plotted below, you can see their composition graph. I found out that 58% of asteroids were carbonaceous, rising to about 70% in the outer main belt, the last bar plot here, suggesting cool, volatile rich conditions during solar system formation. And some cool news I wanted to share, I was able to bring these projects to international stage. And as Myraa already mentioned, I was able to win the second prize at the European Union contest for young scientists for this project. In addition, I've also published 2 peer-reviewed papers. One is a sole author, where I talked about my algorithms that determine the physical properties of asteroid, and one is a co-authored paper about Didymos. And my research is far from over. So far, I've only been taking images in the visible wavelength, but I plan to expand it to both visible and infrared wavelengths so I can better classify silicaneous and metallic asteroids because they have similar albedos. So by looking at their spectra, I'll be able to better differentiate between them. In addition, it'll also help me determine mineral compounds located on the asteroid. I've made my code and project open source so that anyone can try and use it. So thank you so much, and I'd be happy to answer any questions.
Okay, so like we have a few questions in the chat box, and Miss Kriti, you can open the chat box now so that everybody can post their questions.
Yes, I have done that. Thank you so much, Ms. Arushi. Now, Myraa, I would request you to please ask the questions which we have taken earlier.
Yes, we'll go with that first. And before we start the question and answer round, Arushi, that was an amazing presentation. It was just like a loaded burger. I don't know how many of you guys like McDonald's, but it was definitely a loaded burger with information. I really liked how you use that PNG where dinosaurs are talking about we need our answers about asteroids. It was very fun, very informative, and exactly Chris. Thank you so much for that presentation, Arushi. Now we're gonna start with the question and answers round. Please make yourself comfortable. These questions have been asked by me and some of the fellow astronomers as well. So let's get started. So Arushi, okay. Okay, so what is like the primary difference in the composition between C-type, S-type, and M-type asteroids? And how do these differences inform our understanding about the early solar system, like billions and billions years ago?
That's a
Thank
great
you.
question. And actually, for the first part of your question, it's in the name. So C-type asteroids are also referred to as carbonaceous asteroid because carbonaceous elements is their main component, along with a few silicates. Whereas for S-type asteroids, they're normally stony type asteroids, made of stones or made of silicates, whereas metallic asteroids are made of metals. So all in the name. And actually, by determining their composition, I was able to understand a bit more about the early formation of our solar system. Since 70% of the asteroids were carbonaceous in the outer main belt, this suggests very cool and volatile rich conditions during the solar system formation. It suggests that those were formed in cooler environments, whereas silicanous in metallic asteroids, which were closer to the sun, were formed in slightly hotter environments.
All right, thank you so much, Arushi, for your wonderful answer. And yes, this is pretty interesting that all of these asteroid types are based with their names like S for silicon, M for metallic, and C for carbonaceous. The wonders of space are endless, definitely. And going to the next question, what is the estimated size and shape of the asteroid belt? And roughly, how many asteroids are thought to exist within it? Like a rough estimate.
That's a great question. So, the asteroid belt is the distance between Mars and Jupiter. So, asteroids are basically all around that place, and there are millions of asteroids there. So, if you want to know like the exact distance, you would look at the distance of the sun to Jupiter and the sun to Mars, and basically subtract those units. So, for example, if I'm just gonna search it up right now, sun to Mars in AU. So Sun to Mars in AU is about 1.5 astronomical units, while Sun to Jupiter is about 5.2 AU. So you can see that the asteroid belt will be about 3.5 astronomical units wide. And inside there are millions of asteroids ranging from all sizes, all types.
Okay, definitely the asteroid belt is as wide as your achievements, no doubt in that. And okay, proceeding with the next question. What is a near-Earth asteroid, NEA? And how many have been discovered so far? This is similar to the previous question. It's just that we're going more deep into the orbit and talking more about the Earth.
Yeah, so near asteroids are those asteroids which are not in the main belt. These are asteroids because their orbits are uncertain, have brought them very close to the Earth, and that's why we call them near asteroids. So, in particular, these are asteroids which can come 1.3 AU from the Sun. And these asteroids can intersect with the orbit of the Earth, which raises possibilities of collisions. So, about 25,000 of these asteroids have been discovered so far, and more of them continue to be discovered every month. And actually, if we go more in depth, if these asteroids come even closer to Earth, if they come within 20 moon distances to the Earth, even the distance of some of the satellites, then we call them potentially hazardous asteroids. So these are the asteroids which come very close and which could have a huge damage or huge impact probability. So it's very important to monitor these asteroids carefully.
Okay, yeah, that's actually pretty deep. I mean, as deep as a space, this is pretty deep. And thank you so much for that wonderful answer, Arushi. And now, by the time we're proceeding with the next question, everybody please send your questions in the chat box. That would be really appreciated. Okay, so Arushi, what are the technical and economical challenges associated with extracting and processing resources from asteroids? I mean, this is a very debatable topic many students debate on. And since we're talking about asteroid mining, it's very important to know that how does it impact us economically and technically, and how do we extract those resources? And if you have any idea about it, would love to hear your values and insights.
That's a great question. And while that's not the main study of my research, I can definitely share a few insights. So, definitely, there's going to be challenges along the way because extracting resources from asteroids is not a simple feat. First, you have to pick a target asteroid. What type of resources are you looking for? If you're looking for metals, then you'll look at a metallic asteroid, for example. Then you have to actually plan a space mission to go there, which again is not easy. You have to compute the orbit of the asteroid, is it in a feasible distance? And that'll go back again to which target asteroid you have chosen. And you'll have to design a spacecraft and design whatever robotic systems you want to be able to use to actually go and mine into the asteroid. And then once you are, let's say the system has reached the asteroid itself, then how do you want to mine these? That depends on the composition of the asteroid. Sometimes maybe you would drill in the asteroid, but it's a complex task, and it also depends on the strength of the asteroid. It might be easier if it's one monolithic rock, whereas if it's many little rocks held together, which is very hard to pull apart. And once you have your samples, how do you bring it back? And so I think there's going to be technical difficulties all across the way, especially since it's space. It's not like the Earth, there's no gravity, there's no vacuum, it's very different. And for the economic problems, well, obviously, it's going to cost a lot of money to get a spacecraft there. So we have actually gotten samples from asteroids before. If we talk about the Japanese JAXA mission, Hayabusa 2, which went to Ryugu, or the Bennu mission, which actually just came back a while ago. And so definitely it was a hard task, but we have been able to do it. So I think that really sticks out. We have been able to get samples before. So while it is a hard task, it does not remain impossible. Of course, there's going to be a lot of technical issues that you'll have to troubleshoot. It's going to take a lot of money, but it's definitely very possible.
All right, I mean, this was not your expertise, but you gave a very detailed answer, and that too very relatable. That's just amazing, Ms. Arushi. Okay, now here is a question from one of our most interested astronomers, and this is actually pretty interesting in my opinion. What evidence do we have that suggests asteroids could have delivered preabiotic compounds to early Earth? And what implications does this have for origin of life?
Great. So there's two main pointers that point us towards asteroids giving soft elements of life. First is the composition of asteroids, especially the carbonaceous asteroids, because they contain those compounds that are actually found in the Earth nowadays. So it's very likely that some of those compounds were transported to the Earth. Second, asteroid impacts with the Earth happen all the time. Small asteroids happen very regularly, every 4 or 5 months to a year. And whereas some impacts happen less often, but we have seen that asteroid impacts continue to happen every year, which means that asteroids would have had a chance to deliver these compounds to the Earth. And not just asteroids, it's possible that there were even a few comets that impacted the Earth and gave maybe ice water minerals up to the Earth, which is what formed our water today.
Oh, okay. The water part is really definitely something to think about and research on. Now, here's one question for me. How do isotopic studies of meteorites inform us about the thermal and collisional history of their parent bodies?
Yeah, that's a great question. So definitely, if we're able to get meteorites back from once the asteroid is impacted, there's a lot you can find about it. So I won't be able to answer this question directly since I've only been studying asteroids while they're in space. But definitely by looking at the material of the asteroid, how different dents have happened, how the shape has changed since one was in space, if we're able to find that, and being able to perform a detailed study will help you determine a lot about the parent body of the asteroid. For example, if it's only a small chunk of the asteroid which fell into the Earth's atmosphere, you'll be able to determine more about the asteroid which is still in space.
Okay, all right, that's wonderful. I mean, we all are having questions. Like most of us probably will be having questions how to deflect asteroids and stuff. And these questions have been roaming in our heads for a while. And who knows, like one day you could actually find a solution to that, especially your expertise is great and it's mind-boggling. Now we're gonna jump into the chat box directly. So I'm just gonna scroll a bit up. Just give me a moment. So I'm gonna go with the recent questions and then I'm just gonna proceed. And if your question is missed out, please, just pin it again in the chat box because it might be possible that due to all the questions we have in the chat box, I might miss one or two. So the question by Sejan is a question for Miss Arushi. Do you think we can find metals which you can't find on the Earth when mining asteroids?
Definitely, yeah. That's a great question, and the answer is yes. So asteroids actually have very similar materials to what we find on Earth. They have stones, they have metals, they have carbon, and actually all of these materials will probably be able to be found on Earth as well. since we're all coming from the same solar system formation. So, for example, metallic asteroids, since your question was about metals, these can contain gold sometimes, it can contain iron, and all of these are elements that are very commonly found on Earth.
Okay, Sejan, I hope you got the answer to your question. Now this second one that I have in the chat box, it really got to me for some reason. So the way R has asked, what's inside an asteroid? This question has got to me.
That's a great question. So, actually, the interesting thing about asteroids is since they're so small, they're normally not internally differentiated. So, what does that mean? That means because the Earth, we have tectonic plates, we have a core, we have everything, we have different parts. But in the asteroid, it's not the case. Normally, what's on the outside of the asteroid is also on the inside. So, if on the outside you see rocks, then there's probably rocks on the inside. If on the outside of asteroids you see metal, there's probably metal on the inside, which is the cool thing about asteroids, because just from their surface we can find out their whole composition.
Okay, amazing. And this one disclaimer, if I pronounce your name wrong, I'm so sorry because I'm just going according to the spellings and stuff. So if anybody gets if I get your name wrong, I'm so sorry for that. And with that, I proceed on to the next question. Krishika says, I have a doubt. If these asteroids have stayed around for billions of years, won't the evidence of any substances be erased?
Sorry, could you repeat that question? The second part
Yeah,
of it?
sure. I have a doubt. If these asteroids have stayed around for billions of years, won't the evidence of any substances be erased?
That's a great question, and the answer is absolutely not. Because yes, these asteroids have been around for billions and billions of years. But what would if I told you that these asteroids have not changed at all? And this is because this is actually the primordial material from our solar system composition. These asteroids, because there's no vacuuming, there's nothing in space, these asteroids have actually stayed the same since their early formation. So, because they've stayed the same, by looking at their materials now, this is the exact same materials that have happened or that were there billions of years ago. Of course, this might be slightly different if asteroids have collided with other asteroids, which might cause them to break apart into pieces, to join together. But for the most part, all of these asteroids are in their original state from the solar system formation.
Astrotastic. Hope it's crystal clear. Okay, so Arush is wondering, I was wondering what programs and campaigns like IASC and AISCAC. So I think what he means over here is like, what are some other programs that are like ISAC and All India Asteroid Search Campaign? Like any other programs besides them?
Yeah, I've heard of IESC and it's a wonderful program, I think. If any of you guys haven't done it yet, I really suggest you do it. It's a great opportunity for you to try to find moving asteroids on your own in the images that they provide, and it's a really cool experience, so I definitely suggest you try that out. As for other resources, I think one of the main things is more than just these resources. Now that you have these resources, I think an important thing is finding the communities around you, like finding clubs, finding programs. I'm sure most of you are from India, so finding clubs in that area, or even virtually sometimes where people like-minded, like in this iAstronomer club, people are like-minded, people are interested in astronomy, people are interested in asteroid. So I think that's a very big step. I think IASC is probably one of the best ones that are out there. From my mind, I can't think of anything other programs like that. Of course, you can do your own research. Sometimes what I find is best is after you participated in some of these programs, try to think of your own projects. Try to think of something, these programs, a question that they haven't answered, something that you're curious about. And then once you have that question in mind, try to think about the resources you have and are you able to solve that question? You might not have all the expertise you need just yet, but since there's such a big community around you, you'll be able to slowly be able to work towards finding the answer to your question. So I think curiosity is a big part in this. Um, Try to find your own challenges and try to use whatever you know to be able to solve them.
Brilliant. And we were actually doing our, All India Asteroid Search Campaign. We completed with our phase one successfully, with some people getting preliminary discoveries, and we're also heading to phase two.
That's wonderful.
So,
Wow.
yeah. Okay, orbiting to the next question. How many asteroids are formed? This question is by Tanishka. How many asteroids are formed? What happens if a particular asteroid hits another particular asteroids? What is the speed of asteroids? So I think we should break it down with the first part. How are asteroids formed?
Yeah, so asteroids formed during the early formation of our solar system. So we formed the planets, we formed everything, but there were thousands, millions of small rocks that remained that were too small to be considered as planets, but these rocks came from the early formation. And these rocks are what became asteroids, as we know today. And the second part of the question was, sorry, could you repeat it?
Yeah, definitely, no problem at all. What happens if a particular asteroid hits another particular asteroid?
Yeah, definitely. So many things could happen. Asteroid impacts between themselves are relatively common, like they have happened sometimes. And what could normally happen is either both asteroids would be separated, so they would break into several little pieces. And this is especially true if it's a monolithic asteroid, which is just one asteroid, one big rock or one big piece. And whereas if it's like a rubble-based asteroid, there's also a possibility that both asteroids combine. For example, that the impact and then the rocks form around each other, so that both asteroids actually combine with each other and form a bigger asteroid, which may be a slightly different shape.
Okay, so the last part of this question is what is the speed of asteroids?
Asteroids have varying speeds depending on where they are in their orbit. So, for example, if they're closer to the sun, they might have a different orbital period than if they're further from the sun and closer to the outside of our solar system. So, the speed of the asteroids can really depend on a lot of factors. So, there's no one speed of asteroids.
I totally agree with you on that part. Now, we're going to be taking the question of another astronomer who has been waiting for quite some time, Arav. So, his question is, what is the limit of albedo for an asteroid? Known yet.
What is this? Sorry?
What is the limit of albedo for an asteroid? Known yet.
That's a great question. And there's several different types of albedo, which is basically a measure of the reflectivity of the asteroid. So, in my case, I was focused on geometric albedo, which rarely goes above 1. So basically, this is a measure of the reflectivity of the asteroid. So comparing the brightness of the asteroid to a perfectly round diffusing disk of the same size. So normally the biggest that this can become is about 1. So I would say that the highest geometric albedo an asteroid has had is close to 1.
Okay, another follow-up question by Arav is where do asteroids get their elements? I mean, if you have a metallic asteroid, from where do they get their elements? And that's actually a question to question about.
Definitely, yeah, that's a great question. And it all comes down back to the formation of our solar system. Like when everything happened, when the Earth got its materials, when planets got its materials, that's the time when there were so many elements coming together. And that's actually why different asteroids have different types of elements, because there was metallic elements during formation, there were carbonaceous elements, there were stony elements, and all of these came in and formed different types of asteroids.
Okay, perfect. So I hope Arav's questions are clear. Now here's another fascinating question by Pulkit. That is, does asteroids with strong gravity have moons? Oh,
That's a really good question. And the answer is unfortunately no. They do not have moons, but they have what we call moonlets. So I'll explain that in just a second. But the thing is, asteroids have a very small gravitational pull because they're such small objects, which means it's hard for them to have what we call moons. But instead, they have something similar, which is called a moonlet. And this is where we come into binary asteroids. So just as when, for example, there are two asteroids orbiting around the other. So one might not have necessarily a dominant size. One might have a dominant size. It depends on the asteroid system. But this is when two asteroids enter each other's gravitational pull, and since they align, they start orbiting around each other. And this was actually the case with the Didymos system impacted by the Dark mission, where Didymos was the main asteroid, but they also had a moonlet about 1/5 of its size called Dimorphos, which orbited around it.
Okay, wonderful. And also, like, I've been noticing, like, you're getting back-to-back questions, and there's still a lot of questions in the chat box, and you're answering them constantly. Arushi, if you need a breather or a water break, you can just have that. And I mean, because you've been conversating for so long, I mean, your throat might have gone a little sore. So if you just want to grab water, you can do that. I mean,
Perfect. Yeah, great.
okay, so we'll be back after a quick 2 minutes break, I suppose. All fair.
Ah, okay, everyone, just 2 minutes more because Miss Arushi is having a quick water break. You all can also have. She was constantly speaking and telling us many things. Meanwhile, you can post your questions in the chat box which are related to that. Thank you. Just 2 more minutes.
I hope everybody's back, and if you are, please turn on your camera so that we know you're here and present with us. Arushi, you ready? Can we start? Okay,
Definitely.
wonderful. Okay, so I'm actually scrolling a bit up to see the previous questions so that we don't miss any. Um, okay, so I see some questions over here. One is by, okay, so the people who are raising their hands, we're gonna take the raised hand questions at the end. I hope that's completely fine. Okay, let me just see if we have any questions. All right, yeah, one is by Kripitha. Can you suggest any research programs for middle school students?
That's a good question. Research program wise, um, let's see. Um, I think there are definitely lots of research programs that open up in a high school, which you can apply to like from different universities. For middle school itself, I think one of the best things to do is participate in science fairs. Um, because that's an amazing opportunity for you to test your skills in what you could call like the real world, because you get to compete with the other students and you get to actually share your project, you get to learn from others, you get to talk to judges about your project. So I think that's a really good opportunity to do, especially when you're in middle school. Um, because you still have lots of time to make more projects, but it gives you a good idea of what to expect and it gives you a really good head start. So it's amazing that you're here in middle school and that you're already interested in astronomy, which is great. So I definitely think participating in science fairs, even the IASC would be a good idea. And then once you're in high school, which is probably in just a few years now, definitely lots of research opportunities will open up.
Okay, I mean, me and Kripitha, kind of like I had the same question as well, considering I'm also in middle school. So thank you, Kripitha, for asking that question, and thank you, Arushi, for answering that. Okay, so another question is by Anshuman, and he says, Chicxulub was which kind of asteroid?
Chicxulub. Okay, yeah. So that was a very interesting asteroid. That was the asteroid which caused the huge impact. So if I think I have something here. Um okay, yeah, never mind. But I was thinking I had a slide, but I do not. But Chicxulub asteroid was about a 10-kilometer asteroid, and this wiped out the dinosaurs and about 80% of plant species. And this is really a lot. And so this was an asteroid that impacted a long time ago, not just a few thousand years ago, but about 66 million years ago. And that's what caused the wipeout of dinosaurs.
That's true. Okay. Okay, Arushi. So, Anandita says, as you said, Ms. Arushi, that there are a lot of NEOs, near-Earth objects. So will they stay there forever, or they keep on changing their positions with time?
Now that the solar system formation has been long ago, most of the orbits of these asteroids are now fixed. So you could say that the main belt asteroids will most likely stay main belt asteroids. The near-Earth asteroids, near-Earth objects will most likely stay near-Earth asteroids, and that's pretty much the answer. So of course some differences could happen. For example, if two asteroids impact each other, they could cause a difference in each other's orbital period. They could be multiple asteroids instead of one. So that would mean that their orbits will change slightly. But apart from that, all of these orbits will stay the same.
Okay. So Tanishka is back like a boomerang with another question. Have any spacecrafts landed on an asteroid?
Yeah, they have, in fact. In fact, there have been several missions so far. For example, one of these missions is the Hayabusa mission, launched by the Japanese Space Agency, and this is where they went to asteroid Ryugu, and they were able to land on the asteroid, but not just land, they were able to take samples and they were able to bring it back to the Earth, and they're now being studied in the lab. So definitely there have been missions to space to asteroids before, and many more coming up in the future. Another example of a mission was the Bennu asteroid, where NASA launched the OSIRIS-REx mission, which landed on the Bennu asteroid, got samples, and came back just a while ago. So definitely lots of missions have happened, and there are a lot in the pipeline now.
Yeah, definitely. There's a lot of flies by like Lucy and Psyche mission. And Space India also conducted like a whole session on Psyche mission. Okay. Another question by Tanishka. This is like a follow-up question that she wrote as well. What can an asteroid be classified as? Interesting.
Sorry, could you repeat that?
What can an asteroid be classified as?
Um, let's see. That's I'm not able to fully understand the question.
I mean,
Um,
she's trying to say, I suppose. I mean, Tanishka, if you could elaborate that in the chat, that would be great. But as far as I understood, like in what category asteroids are put into?
Asteroids have their own categories. I guess you could also call them minor planets, which is basically another fancy word for asteroids, but they're in their own categories. Since there's so many asteroids around us, they're in their own category.
So can we also say, like, this is a question for me. So can we also say that they're under the category of space rocks? I mean, would that
Yeah,
be alright?
definitely. That's another word for asteroids. Asteroids, space rocks, minor planets. They're all very similar, so definitely you could say they're space rocks.
Okay, perfect. Thank you so much. Okay. So, but what is a potentially hazardous asteroid? I'm not sure the question is by who, because like Miss Kriti sent it to me in the private chat.
This is by Pulkit
Okay, so
Mahajan.
Phuket says like what is a potentially hazardous asteroid? PHA.
Yeah, so a PHA is basically an asteroid which can come between 20 moon distances to the Earth. So these are the ones where their orbit are very close to the Earth, which means that we need to be careful about them. They could impact the Earth. So it's very important to have a firm knowledge about their orbit and even their composition. So an example of one of these asteroids is Apophis, which actually had a close approach, and it was listed as a potentially hazardous asteroid for a long time. And just a few years ago, it came close to the Earth. And as you guys might have heard, in 2028, it's coming back very, very close to the Earth. And it's an amazing opportunity. There's already space missions launched, and you might even be able to see it by naked eye. So it's definitely an opportunity to look forward to.
That is a space alert. Thank you so much. Okay, so I might pronounce this name wrong, so apologies. Snigdha Keshri has a question. How does dark matter or the cosmic rays affect the motion of asteroid? Personally, I love dark matter questions.
That's a great
So yeah,
question.
okay.
Actually, I'm not too sure. Like, of course, there'll be different impacts of these cosmic rays. Um, definitely these impacts, if they were there, they would have happened during the formation of the solar system, and now they would be practically these asteroids would be immune to these impacts. But I think definitely they could have happened during the early formation. Some impacts could have been there in the orbit, but I do not know enough about dark matter to talk about it.
Oh, that's completely okay. Like learning is an endless ocean, or should I say endless void, as we're talking about space. Okay. So, Sarthik has a point over here. What is the rotational speed of an asteroid?
Yeah, different asteroids have different rotation periods and different rotation speeds. It all depends on the asteroid. It depends on their size. It depends on several characteristics or composition. And that's actually one of the things I was measuring in my algorithm. I was able to measure the rotation period of these asteroids because all of these asteroids have different rotation periods, which can help us determine their rotational speed. So yeah, all of them have different rotations, though most of them are in between 2 to 10 hours, which makes it slightly easier to determine because you don't need too long of observations to be able to find it.
Okay, amazing. I mean, somewhere or the other, you and the asteroid are similar because they rotate and you rotate between all fields and you're multitasking at the moment. So, Krishika G has a very interesting question to put forward to you, Arushi. How do asteroids react with the solar wind and other forms of space weather?
That's a really good question. And I would like to bring this to metallic asteroids in particular. So, you know that metal is normally shiny, but at the same time, if you look at the albedo or geometric albedo of the asteroid, you will notice that it's quite low. It's about the same as silicate asteroids. And this all comes down to space weathering, because space weathering basically has created a rustiness in the metal, meaning it's not as bright as it was before and not as shiny, which is why metallic asteroids become more dull.
Okay, all right. They're metallic, but they eventually get dull. I mean, how nature reacts. I mean, okay. So we have another question. So this question, I mean, I would also like to ask you, um, Adwait R says, can any form of life exist on an asteroid? Because I am personally into life research in space, and this question is actually really nice. So if you could please answer that.
Definitely, and yeah, there's definitely always possibilities of life on any object. And since we haven't discovered all of the asteroids yet, there is still a possibility. Of course, that possibility is very slim, but we have seen some organic compounds on these asteroids. We have seen minerals, we have seen carbon. So there's definitely a very slim possibility um that there might be some sort of life, probably not life as we know it, but there could be some sort of living elements.
Okay, I mean, that's pretty exciting. I wish I could just use such a device that I could peek into the asteroid's inner formation and see if like there's any bacteria or any sort of living object there. Okay, so which type of telescope, I was speaking of telescopes, what type of telescope is used to spot asteroids by MD Hani?
So normally lots of telescopes are used. One of the main categories so far is big telescopes. So we only have a few big telescopes across the world in places like South Africa, States, and all around the world, and Spain, Australia. And there's about 8 to 10 of these telescopes, which are specifically meant for observing asteroids. And these are telescopes which basically perform a full survey of the sky. They look all across the sky in their hemisphere and basically are on the lookout for moving objects. And these telescopes are big, so they're about normally 4 to 8 meters wide. So that's what primarily has been used for asteroid characterization in the past. But the purpose of my algorithm was to try to bring asteroid detection to everyone, which is why my algorithm can actually be used by people with any type of telescope, any size telescope, even like if you have a telescope in your backyard, as long as it's about zero point 0.4 or zero point 0.5 meters or higher, my algorithm will be able to allow you to find unknown asteroids.
That is so cool. And that's really generous of you for making it available for all people who have telescopes. Okay, now Tanishka says she has a difficult question for you. Okay, so I haven't read it personally as well. So name an asteroid that is located at the Lagrangian points L4 and L5 and lie in the same orbit as Jupiter?
That's a great question, and I'm gonna admit I have no idea. Um, so that's a great question, and probably Google has the answer. But I do not know enough about the exact points of asteroids to give you that answer.
That is perfectly fine. I mean, we don't know everything. So, okay. Let me just scroll through. Okay. So, Sejan has another question. And he says, this was my question, that if by any chance we come across an asteroid like Chicxulub, which has a chance to collide onto Earth, will a spacecraft somewhat bigger than NASA's DART be able to deflect it?
That's a great question, and the way we choose how to deflect an asteroid comes both to its size and how much warning time we have. So let me just paint a picture for you here. Let's say the size of the asteroid is quite small, like let's say 50 meters, 100 meters, a few hundred meters, and we have a lot of warning time. This opens up many possibilities. We could use a kinetic impactor, which is similar to the DART mission. We could also use a gravity tractor, which is basically when we put an object of high mass right next to the asteroid, and slowly over time the asteroid is attracted to that object and moves closer to it, which means over a long period of time the orbit of the asteroid will slightly change. So if we keep that object in the right position, over the years, it could entirely miss the Earth. But let's say, yeah, we still have a big warning time, but the asteroid becomes bigger, several kilometers wide. So in that case, we have slightly less options. The only option we have is really, or the most popular one, is to use several kinetic impactors because it's very big. So one is probably not going to be enough. But if we use several kinetic impactors to impact the asteroid, we will be able to deflect it. But if we have no warning time at all, let's say we have less than a few years of warning time, we don't have much time to change to orbit of the asteroid at all. So we go to our last resort, which is using nuclear weapons to deflect the asteroid, which is not a good case, preferable case. There are several regulations in space that prevent the usage of these nuclear weapons. And if you, for example, miss the asteroid, you could have huge legal charges. So it's an option to be avoided at all costs.
Okay, so I mean, we're gonna be taking just two more questions, and one of the questions, oh my God, I think I lost the questions due to the pile of questions. Okay, just give me a moment. Okay, yeah, there it is. So, I mean, since the people, I mean, most of them got their questions answered, but since the pile is increasing, we might not be able to cover all the questions. So, Kripita's question will actually help all of us. So how can we contact you on like in future basis? Like if we want to contact you in the future after this webinar. So what is the possible way that we can do so?
You can definitely use email. I can keep my email in the chat if you want. Um, I don't. But it's Arushi, my first name at monitormyplanet.com. So you can, whenever you want, if you have any questions, if you have any queries, if you have any pictures you want to share, please feel free to contact me by that email address.
Okay, wonderful. And before we because we're gonna also, you know, take the raise hand people who are raising their hand and they want to ask their questions on the mic. But before that, I would really like if everybody could please turn on their cameras because we need to make this a starry evening. And let's all be stars with their beautiful smiles and let's all just turn on our cameras. That would be really good. And also speaking of pictures, Arushi, I had kind of like an object to share with you. I found this while I was, you know, doing the asteroid search campaign. I'm just gonna share my screen in just about a moment. Please allow me a minute.
Sure.
Okay. Just 1 second. Okay, perfect. I'll just share. I mean, Zoom has changed this whole outlook. It's just hard for me to navigate
Yeah.
nowadays. Yeah. Okay. So here's the object that I've been wanting to share. So while I was going through the potential asteroids that could be discovered, this thing somehow appeared on my screen. It looks like a bird, looks like a head, and it was actually moving in like a straight line. Basically, it was moving oops. Yeah, it was basically moving like this, and it was just keep on going down and down. So, I mean, do you have any interpretations on this? Because it really
I think,
seems suspicious.
yeah, it's definitely a very weirdly shaped object. I think it has to be noise. You said it was moving in a line, which definitely makes sense if you're looking at it from the camera point of view. So I think it is definitely gonna be noise. There's no object in space that looks like that, unfortunately. But definitely something to do probably with the camera. Probably something maybe went on the camera, which is very possible. Some object, some hair or whatever, which caused this impact. So unfortunately not a space object.
True. I mean, I wrote a mail to the team and they gave me a reply by saying it is an artifact and probably just like you said, a hair or a particle that was there on the camera, but they're not really sure for real. So they might look into it. Thank you so much for answering that. And
Definitely.
so people, if you have any questions, please feel free to raise your hands. Not the physical one, we might not be able to see it, the virtual ones. Okay, we're gonna go serial wise. All right. Sejan, yeah, please go ahead.
So if by any chance, sorry, is there a way we can calculate how fast asteroid Chicxulub was traveling when it collided with Earth? Is there a way we can like calculate how many meters per second it was traveling at?
That's a good question. And this happened so long ago, so it's really hard to see if we can get an exact time measurement. But definitely since we know the rough size of the asteroid, and we know the crater of the asteroid, we can create a rough estimation of how fast the asteroid was going. So maybe if you're interested in that problem, you can take it up as your own challenge. You can try to see, since you know the mass of the asteroid, you can do research about the crater, and you can see if you're able to do it. And I would love to hear later on if you have results.
Okay, thank you.
Okay, next in line we have Krishika.
Krishika, please say your question.
Krishika, I suppose you're muted, so could you please turn on your mic and pose your question? I think she's facing some difficulties. No worries. Anshuman.
My question is, what kind of destruction did Apophis cause?
Could you, I don't think like Arushi heard it because I did not either. Could you please repeat that?
What kind of destruction did Apophis cause?
Anshuman. Okay, like were you able to hear it, Arushi? I mean,
I heard what type of disruptions Apophis, and I didn't hear the last part.
Anshuman, if you could just like type it in the chat box because there's some disturbance. I mean, we're not able to hear you clearly. I think Krishika's back. So would you like to ask your question because you're not able to hear you earlier? Yeah. Could you please okay. Yeah,
Krishika, please speak up, unmute yourself and ask your question, please.
Yeah, I'm sorry I wasn't able to unmute it.
no issues.
Do asteroid has do some asteroids have cores, and if so, like do they have any atmospheres because they're called minor planets?
That's a great question. And in fact, asteroids do not have atmospheres at all. So they're basically you could call them mini planets, mini Earths, but without any atmosphere. So because they have no air, as you call it. So if anytime a human or an astronaut would land on an asteroid, we would need to keep all of our air tanks and everything on because there's no atmosphere that you can breathe in. It's basically similar to the moon, how there's no atmosphere.
I hope that answers your question, Krishika. Jyotirmay, yes, please proceed.
Yeah, so sorry I can't turn on my camera, but I'll just ask a question. So, like, it's not exactly a question, but you told that the strongest and the most effective method to deflect the asteroid would be using nuclear weapons, right?
Yes.
or anything. I mean, it's like not possible, as you said, because of the Outer Space Treaty, that no nuclear weapons should be allowed outside of space. But like also another thing, because nuclear weapons would create it would destroy the asteroid. That would just create a bigger problem because it would be in more fragments. Then why would we use something that we already have 2 to 3 years, which in space terms is less, but sending enough missions can at least deflect it that much that it does not come in the Earth's gravitational field. So, like, I didn't exactly understand your point of nuclear weapons. If you could clarify that.
Sure, that's a great question, and let me try and clarify that for you. So, in terms of space terms, as you said, 2 to 3 years is not enough. For kinetic impactor method to work, or for any of those safer methods to work, we need the asteroid to complete at least one orbit around the sun. And this is so that the the change in orbital period kicks in and it's able to be deflected. Because if we push it while it's in the orbit that's gonna bring it towards the Earth, we have no chance of deflecting it in time. It'll not be able to complete its orbit, and we do not have enough time. And as you said, putting a nuclear weapon does create huge problems. It's not the ideal situation, but if we found that a dangerous asteroid and there was only a few years of warning time, it is the action that we would have to do. There will be many smaller pieces, but likely they will just burn up in the atmosphere if they went towards the Earth. And since this would be considered like a drastic situation, it would be our only way out. So definitely nuclear weapons is not, it's probably at the bottom of the list for preferable deflection techniques. But if there is a very small warning time, then we do not have enough time to send a space mission. The space mission might barely reach in 2 to 3 years' time. And even if it did reach, it will not be enough to change it in one orbit because we need several orbits of the asteroid to be able to actually change its orbital period enough to deflect the Earth and its gravitational pull.
Okay, yeah, I get your point. Like my other thing is, except for kinetic, this like something similar to the NASA DART mission, like putting something of like a large amount of like something with a big mass, they for small asteroids, we should deflect it so it'll orbit around the mass itself. But that, according to me, would be very unethical because if it is, I mean, for us, 100 to 200 meters is kind of a lot to put something in a spacecraft that is heavier than a rock that is equal to the size of a small hill and as heavy as that. So you launching that would require like a very powerful spacecraft. Plus, it will be very unpredictable because the orbital motion of the asteroid will completely change, and it is very unpredictable and highly unlikely for it to be controlled.
Yeah, that's a great point you raised. And definitely, I think what you're talking about is similar to a gravity tractor in a way. Because you're using the mass of the object. And definitely, I think some mission like that will require very, very careful consideration because it's a huge mass that you're launching into space. I think it's a good idea to test it out now because there's no asteroid on collision course, whereas testing it out when we have an actual asteroid. So I think it is a good idea to test it out now. Before we actually have an impact that we have to deal with. Definitely it has to be carefully planned. We have to make sure that it doesn't affect the gravitational pull of any other objects, any other asteroids in the system. So the orbit will also have to be carefully planned. But I think even DART mission was a risky mission. What if it didn't impact the asteroid? What if it impacted another asteroid? What if it made the asteroid on collision course with the Earth? Now that even if it wasn't before. So I think these are all careful considerations that we need to take in, but I think it's important to take these first steps forward so that we know what techniques we have on our hands if there was to be an impact.
Yeah.
I hope that sorts your questions, Jyotirmay.
Yes.
Okay, so we have Anshuman's question in the chat box. So I mean, since we were talking about like we heard only destruction, he asked like, what kind of destruction can opal fist cause?
Um, Could what? Sorry.
Okay, yeah, he said, what kind of destruction can Opal-Fizz cause?
Is that an asteroid name?
I don't know. Yeah, Apple-Fizz. Yeah, that's what he wrote. I mean,
So
I can just like write it to you in the chat
yeah.
box. I mean, let me just post it to you in the chat. Just give
Great.
me 1
So,
moment.
I can answer your question in its whole. I'm not sure about the exact associations of the asteroid. Apophis. Apophis. Oh, okay, Apophis. Yeah, that's a great question. So destruction depends primarily on the size of the asteroid as well as its composition. So I'll give you some small examples. For example, you might remember the Chelyabinsk asteroid, which happened about 11 years ago, where it impacted Russia. And this was about a 10-meter asteroid. It didn't cause too much damage. It definitely injured thousands of people. But if you look at the damage wise, it was very small, it was very local. If the asteroid was, let's say, 100 meters, this would be maybe like a whole city damaged. There might be damages, definitely injuries, definitely the need to evacuate the spot much beforehand because it would be a danger. If the asteroid is even bigger, let's say it's 1 kilometer, then this could cause serious national issues. I'm talking about a whole country here. There could be, and then earthquakes and everything else would be felt all across the world. So definitely it would have a very national impact. And then if it's bigger than 1 kilometer, if it's let's say 10 kilometers, then that would have a huge impact. It would disrupt the whole world. That's the type of asteroid that was like the Chicxulub asteroid, which wiped out the dinosaurs completely. So in the case of Apophis, the size of this asteroid was about 300 meters. So it's relatively small in terms of this. It'll cause some local damage. It might cause a bit of a few cities, but it won't cause any national damage.
That's a splendid answer, Arushi. And now we have our top 3 students who are actually remaining to pose their question. Thank you so much for your patience, guys. So we're going to be taking Pulkit, Arav, and then Tanishka. So starting off with Pulkit, please pose your question.
I have two questions and the first question is, how do namings of asteroids are done?
Were you able to hear that?
No.
He said, like, how is the naming of asteroid done?
Oh, that's a great question. So, asteroids once they're discovered are given like a preliminary designation, which is basically it contains the year, the month in form of numbers, and it also contains what number asteroid is this, what number asteroid has been discovered this day. So if it's like the first asteroid discovered this day, it'll be given 1, second asteroid it'll be given 2. So the preliminary designation is all based on the date, but then afterwards, you might notice some asteroids are named with actual names, and that comes afterwards if these are asteroids which are deemed big asteroids of interest. They're sometimes given a name. And I think for this the observer gets to decide it. Yeah.
All right, so
I have one more question what is the shape of an orbit of an asteroid?
That's a great question. And normally these orbits are elliptical, so like a circle but more elongated. It forms the similar orbital pattern of planets around our system, and it orbits in the exact same way.
so like Arshi, I mean, since we mentioned that the naming system is like asteroid 1 or 2, that's how we name and ABCD. Well, like whenever we're doing Isaac, it's something a bit different. I mean, so are they gonna rename it later, or is it just gonna be like 3 cap letter and 4, I mean, numbers? Or are they
Um,
gonna change it later on?
yeah. So that's the name you can give it if it's when you're detecting it. If it does turn out to be an actual asteroid candidate, the naming will change slightly. You will have a say when it comes to the because it has to follow the same designation as everything.
Yes,
It's gone
definitely.
under the IAU designation. But afterwards, if it's once it's more observations of the asteroid have been taken, we found the orbital period nicely. You may have a say in what we name the asteroid afterwards.
Okay, thank you so much. Arif, the stage is all yours. Please continue with your question.
Me?
Yeah, you, yes.
So, wait. What are Are there any like rogue asteroids, and is any asteroid in our solar system was previously a rogue planet, but just but was like catched by the sun and fell into an orbit around the sun?
Yeah, that's a great question. And definitely, in a way, you could think of near-Earth asteroids as rogue asteroids, asteroids that were originally in a main belt, but then eventually, during the formation, came closer to the Earth. So that's definitely one thing you would call a rogue asteroid. I do not know personally of any asteroids which went towards the sun. There may be, there may not be. I can't answer that for sure, but definitely you could do some research and find out.
Okay. Also, since it's been a while since we have all been on our screens. After taking Tanishka's question, we're gonna be moving towards the wrap of the session. And if you have any questions for Arushi, Arushi, could you please share your mail in the chat? I mean, it will be really helpful for many students.
Sure, I don't think I can send a message in the full chat.
Oh, okay.
Now you can do that, Arushi. I have enabled it, so now you can do that.
Okay, perfect. Then I'll definitely
Okay,
do that.
Tanishka, could you please go ahead with your question real quick?
Yeah, okay. So, is there a space station which is used for the study of asteroids?
Sorry, could you repeat that?
Is there a space station which is used for the studies of asteroids?
Unfortunately, no. Since we only have one space system out there so far, the ISS, it is not primarily based on the knowledge of asteroids. But it would definitely be really cool if we have another space station come up, which was meant for detecting asteroids. That would be definitely really cool. But at the same time, there's also spacecrafts, which have telescopes on them, which have been observing asteroids. One example from Canada is the NeoSat telescope, which has observed asteroids in the past. So definitely there are a few space telescopes that could be observing asteroids.
That's great. I hope that's answered, Tanishka. And for the people who have their hands still raised, we have to head towards the wrap up the session. I'm so sorry. Just please, yeah, Arushi's mail is right there. You can give her a mail and she'll be happy to assist you there. Now, since we have all basically entered into the zone of asteroids, we've studied so much. Why not we have a rapid fire quiz before we end the session so that we stay energized as ever? If that's okay with Arushi, I mean, can we include you as well for the rapid fires?
Sure, yeah, go ahead.
Okay, wonderful. So the fastest finger, who raise their digital hand, will get the option to, or they get the chance to answer the question. And if it's correct, then bingo, you got the right answer. Okay, so there are 5 questions in total that we're gonna be taking today. And shall we get started? But before that, people please lower your hand so that it's completely fair for everybody. Okay, yeah, thank you so much. Okay, so here we're gonna be starting in 3, 2, 1. Question number 1, pretty simple. What is the name of the largest asteroid in the asteroid belt? Fastest finger. Okay, Arush, yeah.
Ceres.
Okay, so your answer was Ceres, right? Okay, I was just confirming, and that is absolutely right. Question number 2. What term is used to describe the small, rocky bodies that orbit the sun primarily between Mars and Jupiter? Aruf, yeah?
Asteroids or comet or meteorites.
Okay, but we're gonna go with the majority that is asteroids because between Mars and Jupiter, that's the asteroid belt, and mainly asteroids are found there. So I mean, your answer is partially correct. That's amazing. Question number 3, we're gonna go with, and please lower your hands, everybody, so that it's fair again. And on this, until I complete the question, please do not raise your hand so that everybody gets an equal chance. I hope you understand. Okay, the third question. I'm gonna speak this question really fast so that let's just see who has the best hearing power. Which spacecraft was the first to visit an asteroid 951 Jaspera in 1991? Arav, okay.
Hayabusa from Japan.
Okay, but anybody else with the answer? Kushika, yeah? Okay, I think she's having some Wi-Fi issues with the aliens. Okay, yeah, you're back. Okay, you're back online, yes.
The first spacecraft to orbit an asteroid or like flew by. Like if
I'm
it's
sorry, could not get your answer.
the if it is flew by, it's Yastra. If to orbit, it is the near Shoemaker.
Okay, I'm so sorry I was not able to hear your answer well, but the answer for this question, according to many sources, is Galileo. Now, the final question of today's quiz is, what is the term for an asteroid that has a close approach to Earth? And we have repeated this many times. Please be the fastest finger, and most like everybody should know about this. Ajay? Yeah?
Myraa, that's Akshay.
Oh, okay, I'm sorry. It's written Akshay over here on your display, so I just called accordingly. Anyways, Akshit, yeah.
Yeah, they're called Near-Earth Asteroids.
Yes, bingo, perfect. So thank you so much for playing the quiz with us. And I just want to say, we should definitely appreciate Arushi for being so spontaneous with her answers. And she was like always giving the answers. And she did, like, if she did not know the answer because it was not her expertise, she still gave the best answers she could. And she tried her best to clarify your questions. And I hope she brought a smile on her face because she's truly an inspiration. With this, I thank you all for being the bright spot in today's galaxy session. Please stay in Space India's orbit or like magnetic field to know more stories, just like Arushi. And who knows, like Arushi will pay a visit to us again, and that would be a hat trick, to be honest. And please remember, if a 14-year-old in grade 9 can do so much in the field of space, coding, algorithms, and stuff, you can definitely do the same. And no doubt, we all are inspired today, definitely. With this, I wrap up our whole grain bread with sauce of love and veggies of knowledge provided by our amazing chef Arushi. Thank you so much for tuning in. This is Myraa Khattar signing off today's session. And over to Miss Kriti.
Thank you so much, Myra. And with this, I would really give my thanks to Miss Arushi for providing us with such an insight related to asteroids. Because we had today's webinar as we are celebrating the Asteroid Day on 30th of June, right? Which is actually celebrated globally. So this is celebrated because of spreading the awareness about the potential risks and what are the opportunities that are presented by the asteroids. So that's why we celebrate this Asteroid Day, which is going to be on 30th of June every year. Okay, so thank you, Arushi, for giving us such a great insight. And this is really a motivating webinar for each of you, all of the participants, because in such a young age, she has done such a great thing. And this is an inspiration for you all to explore more and more. Okay. And thank you so much, Myra, for being a wonderful host for us and hosting this event. Now, to everyone, I would request to switch on their cameras so that we can have a group picture. So that can be a great memory for us. So kindly please switch on your cameras. Okay, so I will be having a group pic. Okay, so with this, I am taking everyone wishing a great night and thank you so much for joining. Thank you, Ms. Sarushi, and thank you, Myra, for joining with us. Thank you so much. Have a good night, everyone.
Thank you so much. Have a great day, Miss Arushi, considering we have different time zones, but all of our bonds are same. That is, we love space. though we are at different places, but same love for the same subject. With this, wishing you clear skies, though here it's raining in my place, but still wishing you clear skies.
Thank you so much. Yeah, it's raining here too. But have a great night, and thank you so much for having me here. It was a wonderful experience.
Same feeling, mutual.